Hello, everybody. Welcome to today's webinar. Today, I'm very excited to announce that we're talking about engineering for software with Dave Farley. Let's start with a little bit of housekeeping. Recording will be emailed to you at the end of the week, so there's no need to record today's session. Questions, please use Zoom Q&A. If you can't use Zoom Q&A, we will be looking for questions on our YouTube channel. You can also join our Octopus community Slack on octopus.com/Slack. Please put your questions into the webinar channel. So today I'm joined by Mr. Dave Farley. Hey Dave, how are you today?
I'm great, thanks. How are you, Derek?
I'm absolutely fantastic. I'm really looking forward to today's session. This is one, I'm a huge fan, Dave, and this is definitely one that I've been looking forward to for some time.
Well, thank you. I'm looking forward to it too.
Definitely. So at this point, it's over to you, Dave.
Thank you. Welcome, everybody. So I've been thinking about engineering for software for a while now, and I think that this might be the kind of post-agile step. I think often, though, when we think about engineering in software terms, we kind of get this confused with kind of a heavyweight bureaucratic process. And it's really not that. I think in other disciplines, if we think about what engineering really means, what it usually means is just the stuff that works. So what's just the stuff that works for software development, and what's the kind of thing that allows us to build better software faster? And that's the stuff that really interests me and the stuff that I want to talk about today. So if you've got bureaucratic heavyweight processes in the back of your mind as I'm trying to convince you that engineering is the right approach, then dismiss those, because I'm hoping to convince you of something different. Let's start by thinking about the way that software projects work. And I think that if software projects were normal things, we'd expect a normal distribution of software project success. We'd expect as many software projects finishing ahead of schedule, delighting their users, and being under budget, as being behind schedule, annoying their users and costing way more than we anticipated. But I don't think that's what we perceive as normal for software development. I think that the curve is much more slanted. And I think this says something interesting and something important. What this kind of says is that we've got the model wrong. The way in which we approach software development there's something wrong with it. What I'm talking about here really is the idea of a paradigm shift. And I love this little GIF animation of two different versions of the orbits of the planets in trying to identify, to talk about the ideas of paradigm shift. On the right-hand side of the screen is the geocentric view of the solar system, the orbits of the planets in the solar system. And this was the model that was held for probably tens of thousands of years, certainly thousands of years. And it assumed that the Earth was at the center of the universe and everything orbited around the Earth. And people would look up at the sky and they'd see the sun going around us and the moon going around us and the stars going around us, and all kind of worked out nicely with that model. And then there were these pesky things called planets. The word planet is derived from an ancient Greek word which means wanderer, because from the perspective of looking up at the sky from the Earth, the planets seem to wander around in the sky in seemingly complicated and random ways. And trying to predict where they're going to be next is difficult. And people started coming up with models like this. Now, as long as you inhabit a solar system like that, then you can't have Newton come along with an inverse square law to figure out how the planets are orbiting. And you can't have, a few centuries later, Einstein coming along with bendy sheets of space-time and general relativity. Those theories simply do not flow from that model. They are not really conceivable within the confines of that model. In order to be able to get to a position where you can have those kinds of more complicated, more valuable, ultimately, ideas, is to have a paradigm shift. You need to shift the perspective with which you view the problem and approach it from a different angle. And that's what happened here. In this case, we had people like Kepler, Copernicus, and Galileo, who came along and set the foundations for saying that the sun's at the center of the universe and that the planets all or rotate around that. Now, that's not correct either, we now know, but it's a much better model and it's much closer to the truth. So we don't necessarily have to have a perfect model to be better, but we do have to have a model that fits the facts better. And that's kind of partly what I'm talking about today. So what does software engineering mean? I think that we tend to think of engineering, as I said, in these sorts of terms, that, you know, it's all the complicated stuff that we can't afford to get wrong, and therefore we're going to think very hard up front and design perfect solutions. This is a mistake. This is wrong. This is a production line. This is a production engineering, and this is not our problem. Software is almost unique in the sense that our product is a stream of digital bytes. Before software, nothing worked like that. And one of the unique advantages of this is that our output, being a stream of bytes, is reproducible perfectly, essentially for free. So at the point at which we've got our stream of bytes that represents our system, we can choose to deploy that, and we can press the deploy button as often as we like and have as many copies of that system as we like, essentially for free. That means that we don't have a production problem. That means that organizing our work around the difficulties of production, which are inherent to building physical things, is a problem that we are solving, a problem that we don't have. And it gives us freedoms that other disciplines don't have either. So I think that's an important first step, recognizing that our problem is not one of production, and therefore production line techniques of trying to regularize the system and regularize the production process don't apply to us. That's not what our discipline is about. If our system needs to be regularized, then the regularized bit is just this. It's just cloning those bytes for free. So looking at other forms of engineering is interesting. It might be informative, but we've got to be kind of careful about the lessons that we take. Software development is not bridge building. There are certainly lessons that we can learn from bridge building, but the logistics of getting steel into the right place isn't one of them. So the production problems aren't part of our challenge. There are other kinds of engineering that are probably a bit closer. I'm currently obsessed watching SpaceX develop reusable rockets that are ultimately intended to take people to land and live on Mars. And the way that they're doing that is interesting from an engineering standpoint. They are moving very quickly and they are trying things out. And as a result, they are developing world-class systems at a rate that people haven't really seen before. The first picture that I just shown was kind of probably about 2 years old now. This picture is current, and there's a huge difference in the quality and design of their spacecraft, and it's moving fast all of the time. They're trying out new parts of their systems, and they're experimenting on them and trying them out on test stands, measuring them and understanding the results. Sometimes things go wrong. Their predictions are mistakes, and there are problems. And then there's some success, and they learn something from the success. It might be a small, simple success, and then stuff will go wrong again. And it's this iterative, experimental approach that is at the heart of real discovery in engineering. And that's really much closer to the kind of problem that we face. We are looking to try and evolve our systems step by step as they grow in complexity. So I would argue that engineering is certainly design engineering, which I think is much closer to what it is that we're doing. But engineering is all about exploration and discovery. And as a corollary of that, then software development is all about exploration and discovery too. That is our job. That is what we're doing. If we need to reproduce what we've done, then we can do that for free. So there's no point us not taking advantage of that. That means that everything that we're doing in some context is new to us. Therefore, we need to focus on the exploration and discovery at the heart of that, which means that we need to start thinking in terms of becoming world-class experts at learning. We need to optimize our thinking and our approach to solving problems with software for learning. That means that there are some fundamentals that we should be applying to achieve that. First of those is iteration. We want to be able to work in small steps so that we can observe the change that we are making, understand whether it's a good or a bad change, and step back from the bad ones and promote the good ones. One of the amazing things about iteration is that you can set a goal, a target to achieve. You can start iterating randomly, and as long as you've got some means of determining whether each step takes you closer or further away from the target, you can hit the target. And you can carry on doing that even if you decide to move the target. This is a tool that is essential for learning. This is the tool that's at the heart of machine learning, science, evolution even. This is how we really solve complex problems, through iteration. The next part of that is feedback. We need to capture information from our iterations and from whatever steps we're taking, so that we can understand what's going on, rely on that information, and again, take the good parts and do more of those and reject the bad parts. We also want to be able to make progress incrementally. Complex systems don't spring fully formed from some genius's mind. They are the product of clever people understanding the problem bit by bit and solving the problem bit by bit. This allows us to tackle more complex problems than we could otherwise imagine. In the 1960s, when NASA landed people on the moon, they didn't start out knowing how to do that. They had a rough plan of the things that the problems that they didn't know how to solve, that they knew that they would need to solve before they got there, and they organized their work around incrementally building towards solving each of those problems at lots of different resolutions of detail. This is how you solve big problems. This is how you approach designing complex systems of any kind. We also need to be able to take the idea of working experimentally seriously. We want to be able to try out our ideas, and the best way to do that, we can learn from science, is to organize our progress, our incremental progress, into a series of small steps so that we can work iteratively, gather feedback, and mine the learning from that feedback. So thinking in terms of how to control the variables so we can understand the messages that we get back, and what the goals are of our experiment, and so on. So organizing our learning into a series of experimental steps is key to be able to do this. And last, we want to be empirical. Engineering is not the same as hardcore science. It's informed by science, but it's much more pragmatic than regular science. The SpaceX people are busy blowing up their rockets, sometimes on purpose, sometimes accidentally, but from each of those experiments, they're learning things. Even though they have sophisticated mathematical models and deep science to back up their thinking, they go and try stuff out. Not very long ago, they decided to change the design of their systems and go from 4mm thick steel to 3mm thick steel. And that's a relative, they were using the same material. They understood the properties of that material, but they built the rocket and they tested it to destruction to see at what point, the welds would give up, or the structural strength, at cryogenic temperatures operated, just to test their models. So we also need to be observing the real world and reacting to what we learn from the real world and feeding that back into our approach to learning as well. Software development is also about building complex systems, and being able to do that means that we must be good at managing that complexity. We can't just treat a complex system as some big ball of mud problem where everything is entangled. We need to think about the techniques that allow to deal with this in pieces so that we can take the small steps that I was talking about before, so that we can organize our work into a series of experiments, so that we can gather feedback on each step as we go. So we need to think about how to manage the complexity to achieve that too. To manage complexity, there are a series of ideas that help us do that too. These ideas may seem fairly fundamental, and that's because they are. I'm going to be talking a fair bit about these ideas for the rest of this presentation. These ideas, I think, are at the heart of our discipline. And if we ignore these ideas, then we build worse software. Good software is modular. We want to be able to organize our systems so that we can work on them and continue to work on them. That means that we need to compartmentalize the problem into pieces. That means that we need to take modularity very seriously and think about it at all resolutions of detail in the design of our systems. In addition to that, a close collaborator with that is the use of abstraction. We'd like to not only divide the system into pieces, we'd like each of those pieces to be kind of hiding some detail behind the boundaries between those pieces. So that means that the boundaries between these modules are a bit more important, and the degree to which each module abstracts the problem from other modules, so that other modules can use the services that this abstract module produces, but not without necessarily understanding all the detail of how it works. That's really what abstraction gives us. One of the key thinking tools that allows us to improve modularity and abstraction in these terms, and other properties that I'm going to be talking about, is separation of concerns. Each part of our system should be focused on doing one thing and doing one thing well. If at the point at which we're writing some code, we realize that it's doing two things, and at that moment, we should be hearing alarm bells going off in our heads and start to think about how we can separate out those things so that they are more independent of one another. That leads on to us building systems that are more loosely coupled and have higher cohesion. All of these ideas are necessary and interact with each other in different ways and reinforce one another. These ideas are probably familiar to you if you've ever worked close to software, but these are the fundamental measures of good systems, to my mind, because what they do, one of the ways in which they allow us to manage the complexity, is that if you have code that exhibits all of these properties, then it allows you to go into that code and change it. And I would describe maintaining our ability to easily, safely, efficiently modify our code is one of the hallmarks of quality that's important. And it's important not just for some technical idea of pure, design purity. It's important in commercial terms. If you can continue to maintain and modify your code, you're able to modify it to better reflect business commercial demands on the system and react to changes in the business or whatever else it is that's growing your understanding of the problem that you're trying to solve. And this allows us to iterate towards better products as well as better designs. So this isn't just about the technicalities of our system. This is how we build products that work better for our customers too. So I would argue that some of the principles of applying engineering thinking to our discipline are that we need to optimize for learning and to manage or limit the complexity. And to do that, we need to start taking really very seriously ideas like controlling the variables so that we're able to run experiments and make better evidence-based decisions on the changing our design or the development, the evolution of our code. I think one of the other lessons that we can kind of learn from science, which is really the granddaddy of optimizing for learning, is never assume that your answers are correct. Start rather from the assumptions that your answers are probably wrong, and then try and figure out how they're wrong. And we do that by falsifying ideas rather than proving them. And this is a very, very powerful idea. A simple example, I can have as many tests as I like, but I can never prove definitively that my software is correct. Alternatively, I can have lots of tests, but if I have one test that fails, I know that my software is not good enough, and therefore I can reject it. Falsification is the strongest stance. And so we can use that as a tool that allows us to test out ideas and to move forwards. Speaking of testing, one of the tools that allows us to use some of these techniques, put some of these properties into high quality code is testability. Starting out with the goal of making our system testable can in itself be a tool to drive quality into our system. And I don't mean that in just some naive sense that it's quality because it's tested. There's more to it than that. I'd like to just explore that idea for a little bit. So what are those ideas that we value in good code? And first of all, fairly obviously, good code has to work. And then there's a bunch of ideas that we've just talked about. Good code is modular. It's loosely coupled. It's highly cohesive. The bits that are closely related are close together. The bits that are less related are further apart. That's a good definition of cohesion and modularity, respectively. Good code has a good separation of concerns, and good code exhibits information hiding or uses abstraction. Now, just for a moment, think about a code base or a system that you are familiar with. Excuse me. And imagine for a moment that system being modular so that you could change it easily in any part without worrying about all of the other parts. It's loosely coupled, so you can change these parts more independently of one another. It's highly cohesive. The bits that you need to work on are in front of you at the point at which you want to do work. It's got a good separation of concerns. At any point when you're looking at the piece of code or the components of the system, it's clear what those pieces are doing. They're focused on one particular job. And it exhibits information hiding. Where it does interact with other parts of the code, there's some kind of abstraction that is divorcing that other part from your concentration at this moment. Now, think about the opposite of that. Think about the same system doing the same things, but it's a big ball of mud. All of the code's jumbled together. It's in maybe one or two big files. It's entangled. Maybe there's no separation of the code. It's not modular in any sense. The data's all global. Which version of those two systems would you work in? I know, I'm absolutely certain that all of us would pick the first version. These are measures of quality that are general, they are generic, and they are applicable to every software system that exists. A system that is modular, loosely coupled, highly cohesive, good separation of concerns, and exhibits information hiding is better than a system that's not. This is a scale that we can use. We can use these as targets to aim for to improve quality in the systems that we build. So what enables us to put that quality into code? Well, it's one thing really, or three things, three versions of one thing. It's down to the skill, experience, and integrity of an individual programmer. It's down to, do I have the skills necessary? Have I got the background that allows me to understand the problem in front of me? And can I be bothered to do it on this day? That's all there is to it, really. And that's one of the reasons why we tend to see such variance between people who are great and people who are not yet great. Test-driven development is something different and is important in this context because it helps us to enhance these ideas. Test-driven development is usually described like this: red, green, refactor. We're going to write a test and see it fail. We're going to write some code to make the test pass and see it pass. And then we're going to modify the test and the code to make sure that they're more generic, more elegant, better designed, nicer to work in, and all of those good things. Now, you'd have to be some kind of strange, crazy person to make your own life difficult. If you're going to start by writing a test, one of the things that you're going to do is you're going to make your own life easier and make it easy to write the test. And that has some implications. The implications are that it amplifies our ability to, it means that it's going to amplify our ability to create testable code. So what does testable code look like? You can probably predict where this is going. It has to work, obviously. What's the point of testing it if it doesn't work? It's modular. It's loosely coupled. It's cohesive. Good separation of concerns. And it exits information hiding. I can't test code in pieces that isn't modular, because I need the pieces to be able to test them independently of one another. If I'm testing the whole system, I'm not really controlling the variables sufficiently. I can't really see what's going on very well. In order to be able to test those pieces more independently, I'd like the setup of each test to be simple. So I don't want to be giving too much detail into the system when I want to test it, the piece of code that I want to test at that point. So I'd prefer my system, my pieces, my components, my units to be relatively loosely coupled with respect to one another, so that I can pull them apart and deal with them more independently. I'd like all of the bits of logic that are closely related to be together in one place, so that when I get a result of testing that one place, it's kind of definitive, and I don't have to worry that, okay, well, it worked over here, but there's this other stuff over there that I have to worry about too. A good separation of concerns means that our tests are focused and targeted at giving us a good answer. And we need to be able to use information hiding, excuse me, abstraction, so that we can get answers back from our code and provide test interactions with other parts without worrying about the detail of those other parts too much. So there's a combination effect here. We can bring the skill, experience, and integrity of a programmer. We can add the amplification effect of using test-driven development to enhance the values of the properties that we ascribe to high quality in code, and that gives us this multiplicative effect. We build systems that have all of these things, but more so. So test-driven development acts as a kind of talent amplifier onto a developer. It's not going to make a bad developer great, but it will make a bad developer better, and it will make a great developer greater. It amplifies the talent of our software development practice. And that's precisely the kind of thing that we would expect from an engineering discipline. Engineering principles do not make bad engineers into great engineers, but they make bad engineers better. They make bad engineers good enough. And I think test-driven development is one of those tools. Let's look at an example of what I'm talking about. This is very, very simple code. It's very straightforward. It's not going to get much more complex than what I'm showing you on the screen there. So we're going to start off with this car, and this car has got a petrol engine, and it's got this function, this method on the car that's called start. And when we start the car, we're going to put the car into neutral. We're going to apply the brakes, and then we're going to start the engine. So let's write a test for this car now. Here's my test. Test should start car engine. We're going to create a new car. We're going to say start. And now there's nothing that we can do. There's no way of telling that the engine has started. We could break encapsulation of the code, but that's a really bad idea. So this car isn't really testable. So now all I'm going to do is focus on the testability, improving the testability of this system. So I'm going to start from the point of view of creating a test. Here's my test. Should start a better car engine. And the thing that I'm trying to achieve is this. I'd like to be able to say at the end of the test, the engine started successfully. So we're going to need to be able to start the car to check that the engine started. We're going to create a better car. And in order to be able to do that, we need access to the engine. So we're going to add an engine this time from outside the better car. And we're going to create a fake engine that allows us to do that. So that's my new test. This is what a fake engine looks like, in case you were wondering. All it's going to do is it's going to record the fact that when we call start on this new better car, then sorry, when we call start on this new fake engine, it just records the fact that start was called, and then we can query that afterwards. And that allows me to write this test. So all I've done is that I've reorganized my code in a way that allows me to make it testable. And that ended up with me creating this better car. So now I've injected the dependency engine into the better car, and the rest of the code is the same. So my better car is different from the original car in this crucial aspect. I've separated out the dependencies. Now let's just think about the implications of that for this car. Why is this a better car? Well, if I wanted to use this car in a production system, I could create the car with a petrol engine, and this is now identical to the previous car. The code is organized in a slightly different way, but it does all of the same things that the original car did, except it was testable. But now my better car is also useful in other contexts. I could create a car with an electric engine, and the code for the better car doesn't change. I could create, if I was some crazy person, a car with a jet engine, and still the code doesn't change. This better car is better in lots of different ways. The code is more modular because it's separated out the focuses of the problem. It's improved abstraction. The car is dealing with the idea of an engine rather than the specifics of a petrol engine. It's more modular because we're not creating the petrol engine. That problem is carried out somewhere else. It's more loosely coupled because now we're dealing with the abstraction of the engine rather than the detail of the engine, and we don't really care how an engine works. We could be doing all sorts of strange things behind the detail of the engine. It's more cohesive because the bits of the code that are related to it being a car are isolated here, and the bits of the code that are about the thing behaving like an engine are somewhere else. Even if it's only at the level of how do you create the engine, that's been moved out somewhere else. So all of these properties that we value in high quality have been amplified by only focusing on the testability of our code. That is a fantastic tool to be able to drive higher quality design into our systems. The other tool that we can use that I mentioned earlier is to work experimentally. And that is to start thinking of each step that we carry out as some form of experiment. We're going to try out things. We want to be able to try out the parts of our systems as well as the whole systems. We want to try out our product choices and see whether they land with our users. And for that, we need to be able to gather feedback and work iteratively and incrementally and all of those other good things. Part of working experimentally is that sometimes things will go wrong and sometimes they'll go right. We're going to make progress in different routes. And the key to enabling that and take advantage of that is to break down our work into a series of small steps. The smaller the steps, the easier it is to spot whether we're doing the right things or the wrong things, and the lower the cost of doing the wrong things when we find out. We'll gather feedback and we'll learn more quickly when things aren't working out as we anticipated. To work experimentally, we need to do all of these things. We need to work in small steps, gather the feedback, predict the results of what's going to come, control the variables so that we're going to understand the messages that we get back from our experiments. So we need to think in terms of how do we control the variables. If our system is big and complex, we'd like to probably be able to test it in smaller pieces. If our product ideas are big and complex, we'd probably be able to want to test those with users in smaller pieces. What's the experiment? What's the lesson that we want to learn? What's the data that we need to collect to be able to understand the results of our experiment? This is what I mean by working experimentally. One of the tools that I think is central to our ability to do that is continuous delivery. Continuous delivery is at the heart of this kind of more engineering-driven approach to developing software. I often present continuous delivery using this picture. It's a series of concentric feedback loops, organized around the development process. At the outside, we're going to optimize from idea to useful software in the hands of our users. At the inside, we've got the really fast cycle of test-driven development. And in between that, we're looking at the releasability of our systems. This is all about trying to organize and free ourselves to work more experimentally. And this is a quote from Richard Feynman, the Nobel Prize-winning physicist. It doesn't matter how intelligent you are. If you guess and that guess can't be backed up by experimental evidence, then it's still only a guess. So we'd like to be able to move beyond only guesswork and into the realm of experimentation. The other tool at our disposal that can help us to achieve some of these things, surprisingly perhaps, is speed. Working to reduce the size of the steps that we can take means that we need to think about the efficiency with which we can take those steps. So very long running cycle times where it takes weeks or months to be able to go from idea to software in the hands of our users give us much less feedback and less valuable feedback than faster, shorter, tighter feedback loops. This is something called the cycle time of two different projects that I worked on. The first one was a bank, and they couldn't make a single line change to the order management system that this software project was in under 103 days. Alternatively, I was involved in building one of the world's highest performance financial exchanges, and we could do the same kind of thing. We could get feedback on the releasability of our software in under an hour. And that gives you a very different picture of what's going on. Continuous delivery is about optimizing for this fast, high quality feedback across the board. In terms of products, we want to get ideas out to our users quickly and efficiently, gather feedback on what our users make of those ideas, and then iterate from there. And technically, we want to be able to make a change to our code and get an answer back in minutes. Is this releasable? And we're going to optimize to do that using speed to drive down the cycle time of our development process. Is a tool that can drive organizational, technical, and cultural changes necessary to achieve continuous delivery. The ultimate goal is that we're trying to create a stable, repeatable, reliable process for releasing software, which means that we're going to automate nearly everything, keep nearly everything under version control, and that starts to give us the tools that allow us to experiment more frequently and with greater freedom. This is one of those tools. This is a deployment pipeline. And what a deployment pipeline does is it allows us to get this feedback very quickly, to iterate really fast, to build incrementally on our ideas, and to gather feedback on those incremental steps and judgment, and gather judgment. We're going to organize our work from commit to a releasable outcome. We're going to try and develop this into to be as efficient a process as we possibly can, so that we're going to get clarity on the releasability of our system multiple times per day. I generally advise my clients to organize their deployment pipelines like this. You have a fast stage, which is focused on continuous integration primarily, and is developer focused. Its job is to answer the question, does this code do what I as a developer think this code does? And our target is to try and gather feedback on that in under 5 minutes. And then the rest of the deployment pipeline, until we get ready to release into production, is to say, is it ready to release into production? We'd like our deployment pipeline to give a definitive answer on the releasability of our change in under an hour. Now, that might sound like a rather extravagant claim, and you may be thinking, well, my software is more complicated than that and can't do this, except that Tesla do this for cars. Tesla can make changes on this kind of timescale, slightly longer than this, to be fair, but still within a working day. SpaceX can do this for space rockets. Google do this for billions of lines of code, and so on. There are many examples of organizations with challenging problems, but this is possible as long as we think that it's important enough. So we're going to organize our work to get really fast feedback on our changes and our results. And that then puts us in a position to be able to release any of the outputs of our deployment pipeline on whatever frequency makes sense in terms of our users and our business. If you'd like to know more about how to solve some of those problems, if you'll forgive me kind of slightly advertising, I run a YouTube channel, and there's a lot more detail on all aspects of building deployment pipelines and many other things to do with software engineering, the testing of these things, the design of these things, and so on. So do check that out. Also, if you'd like to know more about kind of this philosophy of approach, my new book, Modern Software Engineering, goes into this in a lot more detail, and it's getting some great reviews at the moment. It's fairly new. It hasn't been out for very long, but it's getting some great reviews so far. So do check it out if you'd like to know more about the philosophy behind what I've been describing here. Thank you very much, and happy to answer some questions there.
Thank you so much, Dave. That was really cool. I thought that went really well. So thank you so much. I would definitely recommend the book. And also, I'm a huge fan, Dave, of your continuous delivery book as well. Also, it has a picture of the Forth Road Bridge. I don't live that far away from it. So definitely check that out. It is really good. And Dave, obviously, as well, you have some really great YouTube content. Definitely check that out. Yeah, thank you so much. Okay, at this point, I'm going to look at the Q&A. Okay, Dave, I've got you in the hot seat. Shreya is asking, do you believe in 100% test coverage?
I don't think it makes a good target, but I think it's a usual outcome to get fairly close to 100% test coverage if you adopt the kind of disciplined approach to test-driven development that I generally recommend. I think it's not a good target because there's some stuff that's not really worth writing a test for. If I'm writing some code in Java, do I really want to write a test that says, does my getter get the value that's behind it? It just doesn't seem very helpful to me. I think the best way to focus tests is to focus them on the desirable behavior of the piece of software that you're trying to test. And I took quite a lot about trying to design tests that way round and have a very strong behavioral focus, even when we're talking about really fine-grained testing. My preferred approach to test-driven development is a fairly hard-line approach. I tend to prefer not to write a line of code unless I've got a test that demands of me to write that line of code. And I try and adopt that discipline. What that usually ends up with in real-world code bases is somewhere in the mid-90s, somewhere in some high 80s to mid-90s in terms of coverage. But it makes a rotten target. I've seen lots of organizations that set code coverage as a target, and I think that's a mistake, because what you want is that you want the value of test-driven development isn't the tests. The value of test-driven development is the impact that starting with the test has on the design of the code that we write. And so I think that what you want is that you want your development organization, your development teams, individual developers to become obsessed with using tests as a tool to develop their software. And at that point, you don't need to worry about test coverage because you'll have great coverage. If you set it as a target and you incentivize people to achieve some target, what I see all of the time is people just game the system and they write things that aren't tests that aren't very good. I did some consultancy for a company a few years ago who set a target of 80% coverage for all of their teams, and they incentivized all of the teams to hit that target. And we did an analysis of the tests that they had written, and something like 25 to 30% of those tests didn't even have a single assertion in them. So people had just spent time writing tests for the sake of coverage, and I think that's a waste. So I kind of believe in close to 100% coverage, but I think it's a rotten goal to shoot for.
The questions are coming in thick and fast. I don't think we're going to get to all of them, Dave, unfortunately. One thing just to be aware of, If you can, if we don't get to your question today, please email us at community@octopus.com and we'll send over the questions to Dave. But here goes. Shreya is
I'll also
actually
try
asked
and be more concise.
Yeah, well, that's the thing, though. You give very detailed, really great answers. So Shreya has a follow-up question. What's your take on manual testing?
Funnily enough, I've very recently published a video on my YouTube channel. It's calling the role of QA, quality assurance, in agile teams. So do take a look at that, because that goes into some detail of what I think the role of testing, of QA in general, and the manual testing. So the shorthand is I think that all regression testing of any form should be automated, and that the role of manual testing is exploratory. It's to look at new things and just get a human take on new things. That matters when you have a user interface or something like that. I think that for any other things that are just an API or something like that, it's not relevant. You don't need manual testing for those sorts of things, in my opinion. I admit it's a fairly hardline view, but that is the way that I tend to organize things.
I like how you roll, Dave. I like how you roll. Keith is asking, is saying, totally with your comments, totally with you on your comments. I'm trying to push CI/CD in my organization. We are doing CI/CD for new content, but we are hampered delivering because we have many dependencies on monoliths that change a lot slower, so we cannot ship because they are not modular. Any advice?
Yeah, so I think that one of the things that is important about continuous delivery is that it's much more about a philosophy than a kind of hardline set of rules. And so the philosophy is that how do I get myself into a position where my software is always in a releasable state? So that gets you to focus on the right questions. So in this case, the question is that I've got a monolith and I've got other stuff that I'd like to be able to release, even though the change cycle of the monolith is unpleasant. So, okay, so build some insulation between the code that you'd like to change more quickly and the monolith. So one of my favorite approaches at the technical level is using ports and adapters patterns. Write a little adapter between the monolith and the rest of your code and keep that adapter as a translation layer. So it translates between the two. That way, you can build some insulation, however far you want to take it, into that translation layer, maybe even supporting different versions of the API to the monolith. So you could be using an old version while you're developing stuff about new versions of the API that will be coming, and you could use the old version until the new one's available, and all those kinds of things. So it's all possible, and it's how far you want to take it. So those are the kinds of techniques that I'd look to. The other continuous delivery answer in general, so the first one is what I've just described, is you architecturally isolate the components of the system so that they are in essence, in continuous delivery language, independently deployable. The second approach is that you change the scope of evaluation so that all of the code is kept together and you evaluate it whatever changes, wherever the system changes, which works for some kinds of more tightly coupled systems. But in this case, I would recommend the first one.
Thank you for that very detailed answer. That was great. Daniel is asking, and I think I know your opinion on this. Do you think short-lived feature branches are valid in trunk-based continuous deployments?
It depends what we mean by short-lived. If they last for less than a day, then they do have a role in trunk-based development. Well, no, they are acceptable, but I don't think that they add any value. So my preference is trunk-based development. I don't bother creating branches. I'm just going to commit to master. I'm going to commit to my local master. And every time I commit to my local master, I'm going to push that to origin master where my continuous integration runs. That's the way that I prefer to organize things. That gives me the fastest, cleanest, most definitive feedback on my changes. By definition, continuous integration requires us to integrate our changes together at least once per day, which means that if you have a feature branch that lasts for longer than a day, then you can't, by definition, be practicing continuous integration. And continuous integration is kind of the starting point for continuous delivery. So I'll go back to my first answer. It depends what you mean by short-lived. Less than a day, okay, but I don't know why. More than a day, no, they don't really fit.
He did clarify by saying 1 week in the chat. So yeah, I think that, Daniel, is a no.
Yeah.
So Daniel actually has another question. When building CD pipelines, do you think it's pointless having more than one pre-prod environment where you run automated tests, assuming there is no post-deployment manual testing being done?
Again, it depends. It depends on the nature of your testing. I think it's useful to have multiple stages in a deployment pipeline sometimes, but each stage should be adding to the clarity of your picture on the releasability of your code. So for the way that I usually divide up a pipeline is I'm going to have the commit stage, the fast part, the supporting development that we talked about earlier, which is, does the code do what I think as a developer it does? Then an acceptance test stage. And the goal of that is to evaluate the software using little executable specifications for the behavior of the system from the perspective of an external user of the system deployed in a production-like environment. That's enough in terms of evaluating from the point of view of a user. The additions that I might add are things like scalability testing, performance testing, security testing. Those sorts of additions might be useful. I don't think that there's any point rerunning tests. If your tests are good, they ought to be definitive. And if they've run and passed once, that should be enough. So I don't see that there's any utility in duplicating effort in a pipeline. That's just waste. So my preference is to organize it in a way that I can run these things quickly and efficiently and get me really clear feedback on the releasability of our system. And I'll carve it up into separate pre-prod environments, as the questioner called them, only if those pre-prod environments are focused on answering different aspects of the question, is my software releasable?
Great, yeah. And so honestly, we see people with so many environments. It's sometimes a little bit terrifying. It's like, what? You know,
there's one caveat. I'm sorry to interrupt you. There's one caveat that I've just thought of. I might have many environments so I can run these things in parallel. So I kind of separate stages from environments. I might have loads of environments just so that I can kind of farm out my test runs so that I can get answers more quickly.
Thank you so much. Andre is asking, what would be an approach to fast feedback in the dialogue between people? Or what could be what could be time-wise the fastest way of feedback collection from people, especially in distributed stakeholder ecosystems?
So the first thing is try and limit the number of jumps between distributed stakeholder interactions, I suppose. So what that means is that the optimal way of working is that everybody is able to effect the decision on the development and the releasability of our changes are working very closely together, and so there's almost no overhead. Ideally, in the olden days before COVID and so on, we'd all be sitting together in a room, and we could kind of look across and say, "Hey, are you ready to do this?" or whatever, or "Come and look at this." And that's the way to minimize the overhead. Get people sitting close together that work close together. Where you've got distributed teams, then there are other ways of thinking about that. You still want the teams to be working closely together. What you want to try and avoid is things like big time zone differences between different groups, and you want to try and avoid dividing teams up in ways where there's one kind of set of roles in one part of the world and another set of roles in another part of the world. I also have a video on my YouTube channel about this, about working with distributed and remote teams. But the idea is that you want the people that are closely collaborating not to be working with handovers. You want to try and eliminate handovers so that communications is fast, efficient, high bandwidth, and informal. So that we can, we don't need to raise a ticket to raise if we identify a bug, we can just turn to the person that wrote the code and say, "Hey, I've just found a bug in your code. Here's a test that's failing. Shall we work on it together to fix it?" You want those kinds of interactions rather than more formal interactions. And teams that work that way have measurably higher performance in terms of the efficiency of their development practices and the quality of the code that they produce. So that's what we want to aim for. And then it's a matter of structuring our teams to try and achieve those ends. And there are some tricks and stuff you can play to try and mitigate the costs of distributed teams or multi-role teams and so on. Check out the video if you want to know a bit more what I mean about some of those things.
That is honestly, you basically just described how I get into DevOps there, Dave, because I'm a system administrator. I'm ops by trade. But honestly, one of the things that I did was just kind of go and sit with the developers. And honestly, within about a few months, everything was so much better. DevOps by having a beer and just having a bit of collaboration. It's always a good way to do it.
Yes, it is, and it goes quite deep. I spend quite a lot of time on this kind of thing when I'm consulting in big organisations, of helping them to structure the teams to try and minimise any handovers.
It's a very good way of doing it, and you have also people then, and you bring in DevOps teams, and then you create a different silo and all that sort of good stuff. But right, okay. So one last question. Unfortunately, there are a couple just outstanding. We won't get to them today. Andre, I think this is a really great one, Dave, is how would you design learning to attract young generations to engineering?
I think that's one of the things. I mentioned in passing in the video working on building a financial exchange. That was probably the most fun team, the most effective team that I worked on, that I have worked on so far anyway. And one of the things that I'm very proud of was that we were very good at bringing young developers into our team. And when anybody joined our team, but even a young developer straight out of university, on their first day, they would work on software that would be released within a matter of days from then. That's one of the things that continuous delivery gives you. It's also one of the things that pair programming gives you. And so one of the things that I would do to try and make that work is to try and encourage teams, certainly for new hires, certainly absolutely 100% for junior new hires, but more broadly for any work really, is to consider doing pair programming as a way of bringing people into the team culture and get their learning going faster. It's the fastest way that I know of to onboard people for a team. And I think this kind of engineering approach, all of the data says that if you start applying the kind of engineering approach that I'm talking about, is that people enjoy the work more, are less stressed, report a better work-life balance, as well as producing better software. So all of the feedback is that this is a way of enhancing the quality of our experience as developers and development teams, as well as the productivity of our teams and the commercial impact that we can have. And that's kind of, a virtuous circle of reinforcing practices, which is something I think that you would expect if we were able to come up with something that we could genuinely, hand on heart, call engineering for software. How's that for rounding off the conversation?
I think as that goes, that was pretty much perfect. I think you've absolutely nailed it there. Do you know, that is one of my concerns? Like, obviously, I'm in IT now almost 20 years. It's, remote work and COVID is great for me, but when I started out at 23, 22, 23. It's I had a lot of sysadmins or IT managers, etc., that I could lean on. So yeah, it's it's definitely a good way to encourage people to learn.
Yeah.
Okay, so Dave's channel is on youtube.com/continuous delivery. I really do. I love this channel. I personally follow the channel as well. There's a lot of really great content out every week. I would definitely check that out. Yep, and also one thing is Dave has just published a book on modern software engineering. Again, a really great read there. And Dave, thank you very much for writing that. If you do want to talk to us about licenses, please reach out to customer success at octopus.com. We do offer free consultancy to all customers. You can reach out to advice@octopus.com. If you want to understand how I do X with Octopus Deploy, that would be the best people to get in touch with. And you can see all of our webinars, all of our educational content. You can see that on youtube.com/Octopus Deploy. You can stick a thumbs up and subscribe on that as well. All future webinars, hopefully we'll get Dave back as well later in the year. Will be shown there as well. And I know that, Dave, you're regularly posting on your own YouTube as well.
Yes, indeed. And thanks very much for today. Thank you, everyone.
Thank you. And thank you everyone for attending. A recording will be emailed to you on Friday. We do have some sessions coming up where we're talking about managing Octopus Deploy with Terraform. And then Pete Gallagher, he's new in the community team, is coming on with Sarah Lean, and they're going to be talking about getting started with Amazon ECS and Octopus Deploy. Thank you and enjoy the rest of your day.